Hello all, welcome to RISE-Samvaad talk, the first of the three-part series. Today we have the first three PhD students going up for their PhD colloquium. I invite Professor Shivkumar Malapaka, who is the organizer for the PhD colloquium, to introduce the speakers. Thank you.
Thank you, ma'am. Good afternoon, everybody. Welcome to the RISE series of Samvaad talks. The first three talks are by Ameena, Ashraf, Karthika Venkateshan, and Varsha P. Suresh. So the first talk will be coverage criteria based testing of industrial robots by Ameena Ashraf. She is a second year PhD student with Professor Meenakshi D'Souza, and she completed her MTech from Government Engineering College, Idukki, and and is working on the ABB robotics program, if I am not wrong.
Hello, very good afternoon to all. I am glad to be here with you as a part of this RISE 2020 PhD colloquium. Next
up is Karthika Venkateshan. Her title is State-Based Language for Specification of Applications. She is working with Professor Sujit Kumar Chakravarti, and she is working, hers is a part-time PhD. She is working as a Principal Technical Officer at CDAC, Bangalore, and has an ME in Software Engineering from Engineering College, Guindy, Anna University.
Thank you, sir. Happy to be here. Looking forward for the session.
Then we have a talk from Varsha P. Suresh, which is weight calculation approach to improve backtracking for symbolic testing of embedded software. She is also a PhD student under Professor Sujit Kumar Chakravarti. She is also MTech in Computer Science Systems Engineering from Government College Idukki, and also works on ABB project, if I'm not wrong.
I'm happy to present my work in RISE. Thank you.
Yeah, okay. We'll start with Ameena first. We'll take all the three talks. We'll have all the three talks, and the question answer session will be at the end. Thank you.
First of all, thank you all for taking my paper for RISE colloquium. Here, I would like to present my work with my supervisor, Professor Meenakshi D'Souza. So this is a conference paper titled Coverage Criteria Based Testing of Industrial Robots. So I'm mainly working on industrial robots, specifically for the ABB company. So as an introduction, I'm presenting an overview about industrial robots and robotic programming language. So some of our viewers are new to this concept. So as an overview, what is an industrial robot? So unlike another human robots, the industrial robots are just like an arm-like structure. So they are automated and programmable robotic arms, which are capable of movement in 3 or more axes or degrees of freedom. And robotic software is a program. Actually, the robotic program consists of a set of instructions. Mainly, the instruction consists of move instructions like move circular, move linear, move jointly. Some different types of move instructions are there. Actually, a robotic program is a mixture of this type of move instructions. So according to these instructions, the robot will move as decided by the requirements of a user. And specifically, these robotic programming languages are proprietary in nature. For the ABB company, their programming language is Rapid. And for the KUKA industrial robots, they are using KRL. Our work is mainly specified to Rapid programming language. And this is a robot controller architecture. This is the entire framework for the robot controller platform. So these are the industrial robots look like this, just an arm only. They can move in 6 degrees. In 6 ways, they can move in a 3D plane. Then this is the main controller, which controls all the functions of the robot. And this is the teach pendant. This is the programmer side. Programmer side constitute the teach pendant. Teach pendant is also known as flex pendant. This flex pendant is an arm-like structure, which is equipped with a touch screen. We can program the inside the teach pendant also, or we can program from the robot studio in our computer. And Robot Studio is the programming environment which the ABB provides us with their virtual controller, and we can program any ABB robots in the ABB Robot Studio environment. And another one is all these components are connected with the Ethernet connections, and this IO board is for these robots are working with some input-output digital signals. These robots are working based on the values of some input-output system-generated digital input signal and digital output signal, and these are coming from these IO boards. So these IO boards are specifically for input-output, and the status LEDs are for showing the status of some sensors. This is the entire robot control architecture. This robot controller mainly consists of main computer and axis computer and some integrated circuits. And one controller can connect to more than one robot. Here, n robots are connected to the same controller. Then an overview of the rapid programs. As I already said, the rapid programs are the proprietary language for ABB industrial robots. And rapid program contains instructions like move L, that means move linearly from one point to another. Move C, that is move circularly from or move along an arc from one point to another. Move J, which means moving jointly between 2 points. And also this rapid program includes, as other C and Java programs, they include 3 types of routines, procedures, functions, which returns a value, and trap routines. Trap routines mainly deals with the interrupts and events. And also, like other languages, this rapid also supports some variables like num for number, bool for true and false values, and there is an extra special data type which is called a rope target. Rope target is used to specify a point in a 3D plane that we will discuss later. And as I already said, ABB Robot Studio is the programming environment for the programming ABB industrial robots with the help of a PC or a teach pendant. So this is an example of a full rapid program. So the main program, one main procedure is there. The main procedure will call 3 sub procedures, that is user selection, change paper, and pencil sharpener. Actually, this program is for drawing a square or a triangle in a sheet of paper. Actually, the robot is drawing the figure. We have some sheets of paper in our hand, and the robot is drawing figures. So the concept behind the program is when the count of figures in one paper exceeds 10, the change paper is called. The change paper procedure is called. That is, a count is a variable, num variable, and after drawing each figure, the count is incremented by 1, and if it exceeds 10, the change paper procedure is called inside the main, and the paper is changed and the next paper is taken, and continues the drawing. Then pencil sharpener, it is actually the robot is holding a pencil in its tool center point, and if the pencil is blunt, after drawing some figures, normally the pencil is blunt. So at that time, a system generated digital input, that is DI, that is generated by the system itself by using some sensors. So the system will generate that the pencil is blunt, so we have to sharpen the pencil. So the digital input is set to 1. At that time, that routine is called. And the user selection, there is 3 other sub procedures: drawing the square, drawing the triangle, and otherwise you can quit the drawing procedure. This is the entire procedure for drawing some figures on a paper. This is done by the robots according to the user input. So this is the program. So first we have to define the pencil, then the points. Then as I said in the control flow graph, in the main program there is a user selection, and according to the values of count, change paper is called. And according to the values of the digital input signal, the sharpen pencil is called. And inside the user selection, there is an if else condition for drawing square, drawing triangle, otherwise quit. And there is another 2 procedures, 3 procedures are there for drawing the square, drawing the triangle, and cube. Then change paper is also there. And sharpen pencil is nothing but moving the pencil up and down between 2 points. That is the sharpen pencil procedure. This is the complete rapid program. This is this is a move-well instruction. So move-well P10, B200, find T10. This is the syntax of a move-well instruction rapid. That is move linearly from P10. V200 is the speed, that is the velocity. Then T10 is the find means there is no edge cutting in the moving. T10 is the pen tool we are using. That's the meaning of this move instruction. So rapid program is just a mixture of some move instruction based on some variables and some digital input outputs. So these type of rapid programs, we implemented the coverage criteria for testing these types of rapid programs. Mainly we focus on 3 coverages. First one is scenario coverage, second one is robot coverage, and third one is decision coverage. What is scenario coverage means? Scenario means some sequence of events that is occurred based on some sequence of events that is based on some variable values or digital input output values. So, for example, in this program, the sequence of events, there are 4 types of events, that is drawing the square, drawing triangle, then change paper, pencil sharpener. That is 4 sequence of events are there based on the values of count and values of this if-else if statement and values of this digital input output. So in this program, there is 4 sequence of scenarios are there. That is, there are changing paper, sharpening pencil, drawing square, and drawing triangle. So each scenario or sequence of events are the results of some variables or some digital input output values. So we are meeting this scenario coverage by a set of test cases. So for each scenario, we have more than 1 test cases. So each test case will each test case will drive this rapid program to execute in different path of this CFG or data flow graph. Next one is robot coverage. Robot coverage mainly deals with the program which contains more than 1 robot. Here I am not showing that program, because one example of a program is a solar simulation. Solar simulation means there is a conveyor belt and some solar panels are coming from the conveyor belt and 2 robots are there. The first robot takes the good solar chips and give it to the second robot, and the second robot will process it, and like this the first and second robot will work concurrently. So this type of examples, more than 1 robots are working together in a controller. So in this case, the robot coverage is implemented. So robot coverage is also met by a set of test cases for 1 test case for each event by each robot. So if there are 3 robots, 1 test case for each event for the 3 robots. Then next one is the decision coverage. As we all know, this is the classical coverage criteria which we used in the software engineering. So decision points are just some predicates like if, else, if then else, some for loops, while loops, etc. So for an if statement, the program will execute the statement in the true branch or the false branch according to the decision in the if statement. For loop and while loop, the program can skip the loop or program can enter into the loop based on the values of the predicate in the for loop. That are the main decision statement we are taking are if and for loops. And also there are nested predicates are there. Nested predicate means nested if, nested for, nested while, etc. We are also implemented one mechanism for coverage criteria for these type of nested predicates. So for nested predicate, for example, if inside, if another if inside the same, if something like that. So if some nested predicates are there in our rapid program, we are implemented like this. That is, if the first if is there in the nested if statement, if we saw the first if statement, we are creating 1 node. And we are storing that if that predicate that predicate and the type of the predicate in that node. And if the nested if is coming, we are keeping an array of list. That is array of list associated with that node until we are keeping that array until the next block is found. That is, that nested statements are complete. Until the next nested statements complete, we are keeping the array of nodes. So in that tree, we are using a tree-like structure. So they have these member variables, condition type, which stores the type of the condition inside the if statement. Then condition, which stores the condition as a string. Then nested means it is the pointer to the nested statement. Next is the pointer to the next block. False is the pointer when the decision in the statement is false. Prev is the pointer to the pointer to the parent, and prev condition is the if we have some previous condition, it stores all the previous conditions back to back. That is the prev condition. This is our test case generation framework. So the input to our test case generation framework is a syntactically and semantically correct rapid program, which we already tested with our Robot Studio framework. So this rapid program, we are given to the parser. We are given to parser. So this parser will parse all the predicates. If there are n predicates, it will parse all these n predicates. And in normal case, these predicates are in infix form. That is something like a greater than b, something like that. So these predicates will be in that form. But we are using a Z3 SMT solver to find the values of these predicates. So, but this Z3 SMT solver will take the predicates in the prefix format. So we have to convert this infix to prefix. So we are using an intermediate file. That is the infix to prefix converter. And this Z3 SMT solver will give the satisfiable values or unsatisfied. If Z3 gives the satisfiable values, then it will give the test inputs also. Otherwise, it will give unsat. If we get these test inputs are again given to the test scripts. So this test script contains these test inputs and expected outputs. So this test input along with this expected output becomes the test cases. These test cases are we are giving to this test driver. So test driver contains our rapid program and our test cases. So this rapid program will execute the test cases, and after execution, we'll get the result in the even logs. So even logs will match our expected output with the actual output, and if it is passed, it will save and will exit. Otherwise, we have failed. We have to save and repeat the experiment. So these test cases are passed. We can use this in the real-time controllers also. So this is our framework for testing the rapid program. This is the steps in our framework. We are giving the input as a rapid program, which is passed, and where predicates are extracted. Then we are using an open source SMT solver, which is online available. Then if Z3 is satisfiable, it provides the values for our inputs. If Z3 reports unsatisfiable, in that case, we cannot generate the test cases. Then these values we are used as the test cases to verify the rapid programs in the real controller. Then this is one extra thing, that is there is a specific data type called rope target. Rope target is used for specifying a position in 3D plane. That is, but this rope target is an array-like structure which consists of, it is a 4 tuple. That is, it includes, this is the example of a rope target. That is rope target. This is the name of the target. That is target 10. This first tuple means X, Y, Z position of the robot. X, Y, Z. Then the second means the orientation. That is, orientation is symbolized as Q1, Q2, Q3, Q4. That is the orientation. The third one is the axis configuration. That is position of the x-axis, axis 1, axis 2, and axis 4. And this is the number of external axes. That is 6 external axes are there. That is, this rope target is a complex data type. So by using our framework, we cannot directly convert it into the Z3 format. So what we are doing here is we are extracting all these 4 tuples. independently, and we are processing it. And finally, after getting the input test inputs from the Z3, we are combining it into the previous this 4 tuple thing, and we are processing the same. The only difference here, we are extracting this as 4 different components. So we implemented our test case generation framework in 4 different examples. One is the drawing shapes on paper that we already discussed in our PPT. So in that case, 4 number of test cases are generated, and we met the scenario coverage. And the solar simulation is one demo simulation which is already inbuilt in ABB Robot Studio. It also it have 2 robots working concurrently, and there also 4 test cases are generated, and robot coverage is met in that example. The next one is the rope target extraction. In that case, 2 test cases are generated based on some decisions. Then one more example is there, clockwise anti-clockwise path drawing. That is nothing but based on some digital input output values or some count variable, the robot will draw some figures in clockwise or anti-clockwise direction. In that example also, we generated 4 test cases based on this decision coverage. These are the 4 examples that we successfully worked on. So as a conclusion, we have proposed this coverage criteria for test the programs controlling ABB industrial robots, and we are using the open source SMT solver Z3. And our framework is handles many aspects like procedure calls, robot movements, trap routines, input outputs, etc. Then by God's grace, this paper got accepted in the IIIT case 2020, that is to be scheduled on this August last week. So the meeting will be in virtual, and we thank Mr. Rahul Jetli, Mr. Srinivas Patnaik, and Mr. Linus Lakehold for ABB for a useful discussion on testing of these rapid programs. And first of all, I'm thanking my supervisor, Professor Meenakshi D'Souza also. Thank you.
Thank you, Ameena. We now move on to Kartika's presentation.
So good afternoon, everyone. So now I'm going to present the topic stable. It's a state-based language. So we'll be concentrating on the specification and the simulation engine that has been developed for stable. And I'm doing my PhD under Professor Sujit Kumar Chakrabarti. Also for this particular presentation, I'd like to thank Mr. Amogh and Advait, who has contributed for the simulator and the tool development, and also my work in CDAT, so I thank them. Then so first we get into the stable specification. So the stable specification, like as the title says, it's a state-based specification language, but where we began was when we wanted to write specification that supports incremental development and modularization. So initially we began in search for a specification language that would suit specifying web applications. But when we looked into the existing state chart models that are widely used in the industry, like we have StateMate and the traditional Herald state chart and things, where we saw that the variable definitions were there were restrictions on the types of variables, as well as the variables were global. So when we look into some the complicated applications like the current generation web applications, most of the variables need not be in global, but they are in a local space, which are confined to a certain page or functionality. So we thought we could enhance the traditional Herald state chart by introducing local variables, so that when we compared the state chart that was specified in with local variables with the traditional state charts, we could observe that the modularity in the models have increased with using the local variables. And also we have defined the semantics, the types of local variables and the semantics, and also how these variables will interact interact with the basic features of state charts like hierarchical states, transitions, and history. So when we look into the variables definition, so we have come up with three types of variables. One is a local variable, parameter variable, and static variable. So in local variable can be read and written within a state or the substates, and it can be read in an outgoing transition of a state. And static variables can be read or written within a state and substates, but it retains a value even after leaving the state. Parameterized variable is similar to static, but it can be written as in the incoming transition to a state. That is, it could be passed like a parameter into the state of a state chart. And history is basically, it remembers the last active substate of a composite state. So when we have cycles in a state chart, so it remembers which previous atomic state was active. So let us go through this concept with this example. So here if you see SC is a composite state, because composite state comprises of multiple states within them. So S1 and S2 are the direct children of SC, and then S1 is in turn a composite state, whereas S11 is an atomic state because it doesn't have any children. And uh, we also have declarations of variables over here. So here if we see x1, x2 are of type T, which are local variables. And the ones that are in S1, if you see P1 is a parameter variable. So just for the denotion purpose over here, we have represented it in this color, and the ones that are in blue color, they are the static variables, and they follow the scoping rules and the guidelines as discussed earlier. So a parameter variable can be written in the incoming transitions to this particular state S1, and static variable will retain its value even after exiting the state. So these are the basic variable concepts over here. And if you see a state, basically the state machine resides in a state and then it moves to the next state through a transition. So if you see that S11 to S12, we have a transition called, we have when the event E3 arises, so then this particular transition will be taken irrespective of the guard. So the guard is considered as true over here. Then the parameter variable P3 will be assigned to some constant value C5. So this is how we specify this is how the specifications are written in stable. And uh, so when the S1 is a state, S11 is a state which is a child to the state S1. So from this S11 state, we can even trigger the event E5 because it is common to both S1 and S11. So the events that the outgoing events of transitions of state S1 will also apply to all its children. So this is about the state chart language, and also we can see that this particular state we have marked it with H, which means that this state will retain the history. So for example, if I'm entering the state S2 through the event E5, and then if I'm so I will be I'll be automatically entered into the state S21. And if I'm then an event occurs E4, and if I go to S22, after which I exit the state through the event E6, then at any point of time, if I'm going to enter the state S2 again, instead of going to S21, the state will be automatically, the history of the state S2 will be restored, which in case that the S22 will be the state which will be entered. So now when we have transitions in this state machine, so the one more main aspect of the stable specification language is the action code. Action code is nothing but the this the code that has to be executed when the state is entered, or when the state is exited, or when the transition is taken. So an entry code on a state will be written in this format n is equal to n plus 1, which means that on entry the value of n has to be incremented. So an exit code will be can also be specified in the similar format. So when a state is exited, what code has to be executed, and a transition code will be specified in this in the third portion of the transition. That is, we have event, guard, and action. So this is the action code which can be specified as part of transition also. So when we are moving from one state to another state, so for example, if E3 is an event gets raised when the state chart is in state S11, then state S11 will be exited, and so the exit actions of state S11 will get executed. After that, the transition action, if the guard is true, the transition action will get executed. That is, P3 will be assigned to a constant C5, and then we enter into state S12, wherein um, the entry action of state S12 will get executed. So now, basically, whenever a transition happen, we exit from the source state. So exit action, then the transition action, and entry action will get executed. Of this destination, the entry action of the destination will get executed. So what happens if the uh, a destination is a composite state? So if the destination is a composite state like S2, so when an event E5 occurs, it first checks which particular state the state chart is in. So that is, if it is in S11, so S11's exit action will get executed. Then the parent's exit action will get executed. S1's exit action will get executed. And then the transitions action, P2 is assigned to a constant. So this action will get executed. And then we enter into state S2. So the entry action of state S2 will get executed. N is equal to n plus 1 will get executed. And after that, the execution of the S2 one's entry action will happen, because that is a default state. So this is a default entry state. So S2 one's entry action will get executed. Whereas if and then if E4 occurs, and if we are in S22, and after which if we are exiting the state chart, sorry, if we are exiting S2 through some event, then the second time when we enter in S2, instead of executing S21's entry action, S22's entry action will get executed. So this is the execution semantics of the state chart, and also the respective variables will get initialized and assigned accordingly. And also we have certain scoping rules as well. That is, so here if um, a child state, for example S21, can access the local variables of itself as well as its parent. So it could access x1, x2, which is defined in itself, as well as S2's x1, it can access SC's x1 and x2. Whereas a parent state cannot access a variable which has been defined in its child state. So these are the variable scoping policies that we have defined. So these execution semantics. So now that we have a lot of values that has to be stored, and so when we are executing the state chart, we have to maintain the values of all these local variables. So we maintained something called as a value environment. So this value environment is, so basically when we are executing a state chart, we maintain an execution state. So execution state is going to have a value environment. It is going to have the current configuration of the state chart, and also it is going to maintain the history of the state and the value history of the state. So value environment is nothing but it is going to define the mapping between the variable and its value. That is, it is so if there is a variable x1, then it is mapped to value v1. So we maintain a value environment for each and every state, and if that variable is not available in that particular state, then that querying the value environment will give me an undefined value. So the same concept we are also using for type checking. So we maintain the type environment whether the variables correspond to their types. Now we also have the concept of configuration. So configurations of state is nothing but which state is currently active during the execution. So um, it will consider, I mean, it will consist a sequence of states, that is from the parent state to the current atomic state which it is active. So where we have S1 S2 till Sn, where S1 is the current atomic state which is active and Sn is the S2 till Sn are the parent states which are this is so we maintain the entire hierarchy in the configuration. Now we also maintain the history, state history. So that is nothing but whenever during execution, whenever we are going to leave a particular state when an event occurs, so the history, the current child state which was active before the exit is stored in the history of a in the state history. We don't maintain the history of the state, whereas it gets defined when on visiting a state and then exiting a state. Composite state basically, but history is maintained for the composite state. And then we also have value history. Value history is nothing but it is going to not only store which state was exited, but also the value of the variables when that state when we exit that composite state. So that values will also get restored when we are going to come in to the same composite state again for the second time. So this is about the value history. So during the execution of the state chart, we are going to maintain the configuration, environment, state history, and the value history. And when we enter and exit the states, we are going to update these history, the value environments accordingly. So when we are exiting, when we enter a state non-transitive manner, which means that when we are entering an atomic state directly, then it is that we are going to include that state into the configuration, and we are going to store the values like or if x1 to xp are the variables in the state, then we are going to store the values of those variables in the value history environment. And then we are going to execute the entry action. The entry action will change the values of the variables in the environment, and it is going to we are going to add the state yes which has been entered into the configuration. So a non-transitive entry into a particular state will change the environment, the configuration and the environment. So if we are going to enter a state transitively, which means that when we are going to enter a composite state which in turn enters into a set of substates to reach the initial or the default state. So in that case, basically we are going to enter the state transitively. So based on the, like, we are going to enter the default child states of that composite state, and we are going to keep updating the environment and the configuration. And we are also going to like execute the entry action of each and every composite state that we are entering till we reach an atomic state, which will become the which will which will also be added to the configuration. So till we reach the atomic state, we keep entering transitively and keep updating the environments. And the transitions, so when we are when a transition is getting executed, so we fetch the values from the value environments as well as from the we fetch the values from the value environments, and then we are going to execute the transition. So now so by default, certain set of variables will be initialized, which will be like specified in the model. Like we saw n of 0, which was a static variable, which is initialized to 0. And we can also have a set of variables which are uninitialized, which are like undefined variables, which may further get defined during the execution of the state chart. And then we define the type environment as well as we define the history. So the history is like is the initial state of when the state has not been entered before. The history is the initial state of the composite state in which we have enabled the when which we have specified that history has to be maintained. And then we are also creating the environment is going to be the same as the state history. Sorry, it is going to be same as the value history, and we are going to maintain the values over there. And then this is how the initialization of the state chart happens. So when there is a transition that is happening, we are going to exit the source state basically, and we are going to enter the destination state. So accordingly, we will be updating the history value environments. So by transitively exiting the source state and transitively entering into the destination state. So so that's what happens over here. That is what has been specified over here. So if the event is so here so basically in a state chart, the transitions gets triggered only when an event occurs. So whenever when we process a particular event, there will be multiple transitions that may correspond to a certain event. And we understand whether that particular transition has to be enabled depending on whether the guard of the transition is true. So based on that, we can pick a particular transition for which the guard evaluates to true, and then on an event occurs, we update the value and history environment. So when there is an event failure, the environments, the values doesn't get changed over here. So if we are going to not have any event, we basically halt the execution, the state execution. So this is the execution semantics. So basically we initialize the state chart and process the set of events that are there, that we maintain in the event queue, and then we run that's what is going to change the environments that we are going to maintain. So this is the operational semantics of the stable specification. And so the simulation engine that we have developed is actually we have implemented all these semantics on how to maintain the value environment, how to define them, and all the scoping rules and everything. So now the configuration is also maintained. So this particular simulation engine can be executed in 3 modes, that is pre-event mode in steps, which means that we give that a sequence of events, and then it could be executed at one shot, or it could be executed in steps. Or the simulation engine also provides a way that it goes and it waits for the user input for providing an event. So we can give the event that has to be triggered at a particular point from the set of events that are and then the simulation engine will behave accordingly. So this simulation engine can be used to run the automated test to identify the issues in specification. This will be quite useful when we have to test the specification on a subset of inputs. Now, this particular the implementation that we have done. So it takes a stable specification, it parses the specification, and it type checks the specification. It identifies the type and scope errors from the type environment and the type environment that it maintains, and also the AST that comes out of this specification, we give it to the simulation engine, which is going to maintain the respective environments, and it will be it can run in different modes, that is pre-ordered, one-step, and event queue mode. So wherein the events get processed sequentially, and the variables can be either maintained in a concrete way or a symbolic way. So by running the simulation engine, we will be able to find the issues and the execution trace in which the issues occur. So one such issues that we have handled in the simulation engine is a non-determinism. So if you see this particular example, so non-determinism is a concept that is quite inherent to state charts, but it is good for us to detect, because in a large specification, it is possible that a non-determinism has been specified unintentionally. So here, if we see this particular state chart, we have an x as a variable, local variable, and it on entry it is taken as an input. So now we go into this particular state A, substate A. So here, when an event, the transition T1 specifies that when an event E1 occurs and if x less than 10, then x should be incremented and it has to go the destination status A again. And then we also have one more transition T2, which is going to say that there is if an event E1 occurs and x is less than 0, then you have to go to state B. So as you can see, when the state is, when the current configuration is in substate A, and when an event E1 occurs, there are two transitions that will get enabled, because for both the guard conditions will be true for any input that is less than 10. X less than 10 also will be true, x less than 0 also will be true. So now in order to identify this, we have to basically identify that when an event occurs, whether the guards are all true. So in this case, in this example, like we have to check whether guard 1 and guard 2 are true, or guard 2 and guard 3 are true, or guard 1 and guard 3 are true. So if any of these things is true, so in that case the non-determinism occurs. So this particular thing can be identified through simulation, and our simulation engine is available at this GitHub repository. You can go through that. So this is about the stable specification, and we have a paper published in ISEC recently, 2020. And I thank my professor and all of you for giving this opportunity for presenting this work. Thank you.
Thank you, Kartika. Varsha, can you start now?
Good afternoon, all. Today I'll be presenting my work on weight calculation strategy to improve backtracking in symbolic execution of embedded softwares. My supervisor is Professor Sujit Kumar Chakraborty. So this will be the topics which will be covered during this talk. So as in today's machine and plant automation systems being shifted from mechanics and or electronics into software, all the quality assurance measures which are well known in the area of software engineering, such as software testing, static analysis, code inspection, model checking, etc., are like receiving increased attention in the development of embedded softwares, industrial automation systems, etc. So here we were taking a quality assurance measure like symbolic execution. So first, what is symbolic execution? Here, if we have a program and we need to find out the test input value, which will take me to this statement, the error. So we can do it by symbolic execution. So first we'll take the control flow graph of the program, and then what we'll do is we'll associate each input variable to a symbol. So here A, B are the two input variables, and we associate each input variable to symbol A, B. So C will be 2 into B. Then what we'll do is we'll take, in order to reach this point, we need to satisfy the true part of C equal to A and true part of A greater than B. So which will result in a path constraint. That is this one. So if we are able to solve this constraint, we'll get values for A and B, which will take us to this statement. So for solving this constraint, we'll be using a SMT solver, like C3. So this is what symbolic execution is. So this approach has some fundamental challenges. Out of it is path explosion and complex constraint. If we are using the symbolic execution in real world programs, then we have a large number of program paths. So symbolic execution on each of these program paths can cause high computational overhead. So there have been several works which are used to optimize or reduce, like in order to reach the target edge, different search strategies have been devised. One other challenge is complex constraint. Sometimes the solver won't be able to handle some complex constraints, which includes mathematical functions like sine, log, etc. So here in our work, we are concentrating on optimizing this problem of path explosion. So what will be the reasons for path explosion? All of us know that branches. So each branch introduces two conditions, like two true, false. So each branches will result in exponential growth of paths. Similarly, loops and function calls. So we are introducing we are working on embedded systems. So several tools are there which uses this symbolic execution, like CLI, Qt, JQt, etc., which are used to generate test cases. So all of them are focusing on coverage of the code. But if you are looking into embedded system, there is one property, like they involve interaction with other physical subsystems. So at some point, more than coverage, we need to reduce the cost of testing. So this can be accomplished if we can reduce the test sequence length generated. So one framework, SymTest framework, is utilizing this fact, like to generate shorter test sequences, and thus reduces cost of testing. So next I'll explain what SymTest is. So here we'll have the control flow graph of the program under test. From this, we'll find out a control flow path, and out of which we'll choose a syntactically shortest path. And then we'll perform symbolic execution, which I explained before. The same symbolic execution is performed on this path, which will give us a path predicate. And we'll solve this path predicate using an SMT solver. And if the predicate is satisfiable, we'll get values. If it is not satisfiable, we need to handle unsatisfiably, so that we'll get another path which will take us to an error. So for that, we'll be using backtracking and heuristics. So one of the challenge of this SymTest approach was that if the initial path obtained is satisfiable, it ensures that it is the shortest path, the SymTest approach. But if the initial path, the first path obtained is not satisfiable, we will backtrack. We will backtrack by one node. the path obtained after this backtracking does not ensure optimal path. So this was a problem with SymTest. So for example, here this is a control flow graph of a program, and I want to get test inputs which will take me to the edge E15. So initial path will be E1, E2, E3, E4, E6, E9, E11, E13, E15, E17. So it is found to be unsatisfiable. So as per SymTest, it needs to backtrack to the previous decision nodes. So these are the decision nodes. First, I'll backtrack to this node, and it will lead me another path. But again, this path is also found to be unsatisfiable. Then again, I need to backtrack to this node, which will result in another path that is also unsatisfiable. Then backtrack to this node, which will result me another path that is satisfiable. So if I'm able to backtrack not by one node, by more than one node, it will help me, right? So we come up with a strategy, weight calculation strategy, which supports backtracking by more than one decision node. So here we are using the history of previous runs. In this program, we need to reach the target edge E15. So there are two factors which contributes to the weight calculation, the probability and the length. By probability, we mean, here for example, I had 3 previous runs and my target edge is E15. So from node x less than 90, that is the edge E3. So here 3 paths are going through x less than 90, out of which 2 paths, that is third and 2 is going through E15. So the probability 2 by 3. But if the node is x less than 50, only one path is going through E4 and E15. So 1 by 3. So this is how we calculate the probability for each of the decision nodes. So the probability, if n is the current decision node and tj is the target edge, like there can be one or more target edges. We are considering only one target edge now. So the current decision node, one target edge, the probability to reach this target edge is number of all parts that covers the decision node and the target edge by total number of paths. So this is how we calculate the probability. Then the next factor is length. So here length means the number of iteration of this outer loop. This is what we call length. So in order to keep the test sequence shorter, the length should be minimum. So this is how we calculate length for each of the target edge. So for that, we are the overall effect of the length should such that it decrements the weight value of the decision node. So by this probability and length, we'll be able to calculate weight for, we'll be able to calculate individual weight contributed by one target edge. So we'll calculate the composed weight for each of the target edges, which will give the overall weight for each of the decision nodes. But by calculating only the composed weight is not serving our purpose, because even there is chance of more than one target edge, right? So if there is more than one target edge, it can take me to a node which have maximum composed weight, but still it gives me more number of iterations. So in order to cope with this, we are performing ordering. So in ordering, what we are focusing is to get to a backtracking point which will give us shorter test sequences. So for here, we'll construct a weighted graph for that. where each vertex is the backtracking point and the target edges. And each edge represents the weight. So if the weight to reach I to J, like BI to T3 is greater than T3 to BI, then we will have an edge from here. So finally, we'll perform ordering on this weighted graph, and we'll take the backtracking node which have larger value. So using the weight and ordering, we'll get a backtracking point which helps us to backtrack by more than one decision node. So this is the work, and this work is implemented with SymTest, the framework, and it is found that the SymTest approach with this weight calculation is giving better results compared to SymTest. Now, what I'm focusing is on experimenting like against state-of-art tools like CLE, CREST, etc., and also how to implement a variation of this strategy by using reinforcement learning. So I would like to thank Rahul Jetli and Atul Suresh who have been there, who have been contributed this work. Yeah, thank you.
Thank you, Varsha. We have a few questions in the chat. First to Ameena. Yeah, you have a question in the chat from Professor Sujit. It says on slide 15, the infix to prefix conversion is an implementation detail. The input expression can be read and fed directly to the SMT solver through an API call. Sujit, do you want to go?
Hi, Ameena, I think you understand the question, right?
Yes, I understood that.
Right. So that would be so it doesn't change anything in the main part of the work, just that.
Okay, that portion only.
That's the only thing.
Okay.
There's a question for Kartika.
Yeah.
The question is from Jaya, Professor Jaya. What applications or programming language environments can stable be used with? Sorry if I missed the detail in your talk. Is the simulation environment PL agnostic?
Okay, so the language is designed as a specification language, and the action language that we are using over there, we want to use abstract action language in the specifications, and we want to verify it in the specification stage itself. So the simulation engine also uses the same abstract language with some basic data types, but also having provision to create. So that's how we are proceeding. That's the direction.
Okay, and the second part is the simulation environment PL agnostic?
No, actually, that's what it works on abstract action language.
Oh, okay.
May I just chip in here?
Yeah,
Yes.
please.
So the way the framework is being architected is that it will eventually evolve into a PL agnostic environment. So it will be possible to. So there are 2-3 directions in which we are going. Number one is we are developing a translator, a compiler, which will take a complete model written in this language and will be able to generate target imperative code in Java or C++, etc. Directly, which can then be either executed or verified, etc., using off-the-shelf tools. That's one thing. The other thing is we are architecting the overall modeling framework in such a way that various off-the-shelf programming language can be plugged in as action languages, and the whole thing will run seamlessly. So both those design aims are there for future. Thank you.
Okay, thank you.
Thanks, Karthik. And Sujit.
Yeah, there's one question for Varsha. The question is the issue from Meenakshi, Professor Meenakshi ma'am, is the issue regarding backtracking an unsolved problem? Maybe you should check other symbolic execution tools to see if it is solved. That's for Varsha.
Yes, sir. I have like went through different symbolic execution tools. So they are using different kind of search strategy. So if one of the tool is using a particular search strategy and solving the same issue, then the other tool will be approaching the same problem in a different manner. So I think in order to optimize this problem, different tools are taking different approaches, so that this tool will be better compared to other tools. So this is what I understood while going through different tools.
Okay. Are there?
Sorry, Varsha, Meenakshi here. I was just wondering, so if each tool is taking a different approach, why can't one of those approaches be used here? Why do we need yet another approach? And how will you show that this is better? I mean, we should probably take those benchmarks and show it, or how will we show that it's a new approach and it's better than all others?
Yeah, one of the problem which I face is that most of the tools are focusing on coverage. Rather than reaching a target edge, most of the tools like Glee are focusing on covering the all code. So the search strategy used in such tools are they have in mind, so that they need to cover more code in less time. That is their policy. But for us, our intention is little bit different. We need to cover particular target edges together. We are not focusing on coverage. So directly adopting coverage optimized search strategy or other search strategies which is used in other tools will not help here, I think.
So I guess it was a good set of talks, and we congratulate the PhD candidates for the publications they have had on their PhD work. So let's give them a big round of applause.